Now we start with modeling of mechanical systems in state space. The question has come in my mind, why we are doing the modeling of mechanical system, why it is needed. For example, I am taking, let us say this is a pendulum. A pendulum, if you make invert it, okay, what will happen? It is fall down. So here what happened? We have to develop certain controller, or we have to design a controller which will stabilize this pendulum, inverted pendulum. So how to make stabilization? For stabilization purpose, we required a modeling. See, mechanical system involves pendulum, robotic arms, various type of mass damper systems. So here we require to do model. Let us say another example, robotic arm. What is the purpose of robotic arm? Is to pick the object and place it. For example, this is my arm and this is a motor. His motor is here, and as this motor rotate, this arm will move. So this is a position of a motor, initial position of a arm, and it has to move here. But what happened if you move like this, but this arm making oscillations? So what happened when arm making the oscillations, the placing of the object may not be proper. Therefore, to reduce these vibrations, oscillations, we need a controller, and for the controller, when we design controller, whenever we have model, therefore the modeling of a system, particularly mechanical system, is very much important. Now we will see how will you model a mechanical system. So in this we will study introduction, modeling of mechanical systems using state space, free body diagram approach. Third, modeling of mechanical system using state space, nodal analysis approach. The mechanical system involves two types of motion, one is called translation motion and other is called rotational motion. What is meant by translation motion? The translation motion is along the straight line or maybe along the curved path, and rotational motion be motion along the axis, particularly rotational motion, let us say motor or motor which using robotic arm, that also a rotational motion. So when the translation motion is there, we apply a force, but when comes rotational, it comes a torque. Just like electrical system, we have resistor, inductor and capacitor. Here also in a mechanical engineering and mechanical system, the elements are represented as mass, spring, damper, that is in case of translation motion, and in case of rotational motion it is inertia, spring and damper, only changes mass. Now how to define the mass? It is defined as the property of an element that stores kinetic energy, therefore it is analogous to inductance. So how do you represent it mathematically? So here I am showing, this is mass m, force F of t, and here output y of t. So here this y of t is a displacement, y of t is displacement and f of t. So this f of t equal to m into a of t, f equals to ma, this standard expression you might have studied in physics. So here f of t equals to m into a of t is accelerations. So how do you write down the acceleration with respect to velocity? So first of all write m equal to d square by dt square into y of t, that is equal to m d of t into v of t, that is a displacement and this is velocity. Now coming to spring, it is defined as the property of an element that stores a potential energy. It is analogous to capacitor in electrical circuit, and it shows linear relationship between force and displacement. Now how do you represent this spring in mathematical way? Let's just see it. So here I am showing a spring, a force F of t and displacement y of t. So, this F of t equal to k into y of t. This is the mathematical representation of a spring. Now, come to damper. Damper means just like as a frictions which oppose the motion. So, here friction opposes the motion. It is also called as dashpot. It shows the linear relationship between the force and velocity. So, now we represent it mathematically. So, here force F of t and this F of t that is equal to B dy of t by dt. So, this is the representation of mass, spring and damper. Now, we will see an example, and by means of this example we can determine state space model of a mechanical system. So, the first example is related to simple system with the involvement of only 3 elements, spring, mass, damper, and then we will take the higher order systems, that is many masses, many springs and dampers have been involved. We will start with the first system. This is spring, this is damper, this is mass m, this is force applied, this is k, this is b, and displacement is we are showing as y of t. So, we have mass, let us say we have mass and we apply force to this mass. So, when we apply force to this mass, it is opposes by the spring and damper. So, here this is a damper and spring. So, it is opposing. Therefore, if we draw the free body diagram of this one, you will get the free body diagram like this. This is mass m, we apply force F and it is opposes by k into y of t, that is spring force, and here it is b d of dt of y of t. So, now this is the FBD, free body diagram. And now we have to write down the equations. So, equation means we write down as force F minus k, this is opposing. So, we write down as k y of t minus b differentiation of t into y of t equal to m d square by dt square into y of t. That is, this equation we can write down as in this way. Now, once this equation we have got, now we have to determine its state space model. Now, we have to assume the state. So, how many states are there? States is based on the displacement. See, here there is only one displacement, that is yt. So, we will take one state, first state as x1. So, we can write down as state x1 equal to y of t. Then another state x2 we can write down as y dot of t, and this x2 dot equal to y double dot t. So, therefore, if you see these particular equations, now we have to represent this equation in a state space form. So, this states we have to merge here. So, we will get, so here we will get m x2 dot equal to minus k into x1 of t minus b x2 x2 of t plus f of t. So, here this is m. So, here y double dot t. So, y double dot t equals to x2 dot minus k. What is y of t equals to x1 of t, and here is b. This is y dot t equals to x2 of t and this f of t. Now, we take x dot equals to minus k by m into x1 of t minus b by m into x2 of t plus f of t. And what about x1 dot? Where x1 dot, that is equals to x2. So, finally, we write down this equation in terms of x dot equal to ax plus bu. So, here we write down this equation as x1 dot x2 dot. So, what is x1 dot equal to x2? So, we write down as 0 1 x1 x2, and now this is about into u. So, x1 dot equals to, so terms of u is 0. Now, about x2 dot. So, you will see what is x2 dot, that is here x2 dot equals to minus k by m into x1 of t, b by m into x2 of t, f of t. So, here this is basically d square y of t is like this x2 dot of t. So, we write down as minus k by m minus b by m and here 1 by m, and this is u, basically input is your function f of t. So, you will just see here. So, here x2 dot equal to k by m into x1 of t, and what about the terms of x2 of t is minus b by m. So, here we written minus b by m, and terms of f of t, here if you divide by this is become f of t divided by m. So, finally, the equation is x2 dot equals to minus k by m into x1 of t, b by m into x2 of t, f by m f of t, that is 1 by m into f of t. So, we are written like this. Now, what is the output? Output y equal to x1, therefore, this y equal to 1 0 x1 x2. So, this is the state space model of a mechanical system where there is involvement of spring, mass and damper. Now, what we do? We have to draw its block diagram. So, how many states are there? 2 states. So, how many integrators are required? There are 2 integrators are required. So, I will show 2 integrators here, integrator 1, this is integrator 2. Now, here output y, then here is this integrator, here is x, here is x1, here is x1 dot equal to x2. Now, here is x2, now here is a summing block, and here is the force is coming f of t, and here is basically a block of 1 by m. So, here x2 dot equal to 1 by m into f of t, and here we have to show minus k by m, k of m, k by m of x1, then here minus b of m into x2. So, y equal to x1, and this is x2 dot, x2 dot equal to minus b by m into x2, then minus k by m into x1 plus 1 by into f of t. So, this is a state space model as well as the block diagram of a mechanical systems. Now, we will start with another example. Now, here we are taking the 2 mass m1 and m2, along with we have spring and damper. So, I am drawing the diagram of the system. just here. Now here is a damper. Then we have mass m1, this is spring K. Now this is mass m2 and this force F of t, and this is displacement y of t, that is y2 of t, and here displacement y1 of t. So, you can write down y2, y1 of t, y2 of t, or simply y1 and y2, there is no issues. So, now here we are neglecting the gravity effect and we have to represent in a state space form. So, here force is applied, the force applied F of t is opposed by this spring as well as this damper, and because of that there are two displacement, one displacement is y1 t and another displacement is y2 of t. So, now what we do, we draw a free body diagram for both mass m1 as well as mass m2. So, for mass m1, if you see, is there force acting? No, your force acting is 0 because force acting to m2 only. Therefore, but this m1 opposes this force F of t. Therefore, it will show in these directions equals to b y1 dot, that is y1 t or simply y1 equals to y1 dot. Then here this spring is proportional to displacement, whereas damper proportional to velocity, that is why we have shown y1 dot. So, here we write k y1 minus y2, this spring involvement of two displacement y1 and y2. So, we have written k y1 y2. Now, coming to m2, this m2. So, m2 the force F of t has been applied and it has been opposed by only spring k y2 minus y1. Now, next step, we have to write the force equation for both mass m1 and for mass m2. Now, for mass m1, so for m1, so this m1 into y1 double dot, because for mass m1 we represent it in terms of accelerations, force applied to mass equals m into a is acceleration. So, displacement to 2 dot for y1 we have shown, plus b into y1 dot plus k y1 minus y2 equal to 0. This is equation number 1. Okay, so, m1 y double dot plus b y1 dot k y1 minus y2 equal to 0. Then for m2, so for m2 applied force is F of t, it has been opposed by the own mass, that is m2 y2 double dot minus k, this k y2 minus y1 equal to 0, and finally this equation can be written as F of t equal to m2 y2 double dot plus k y2 minus y1. This is equation number 2. Now, this equation we can again reformulate it as, that is m1 y1 double dot plus b y1 dot plus k y1 minus y2 equal to 0. This is equation number 3, and equation number 4 is m2 y2 double dot plus k y2 minus y1 equal to F of t. This is equation number 4. So, we have got 4 equations, and but we are mainly concerned with equation 3 and 4. Now we have to assume the states. Now how many states we can assume? So here there are 2 displacements, therefore definitely we can take 2 states for displacement, and then you will find that these are terms, there is a term involvement of your d square, that means another states we have to take, that means that here you will find that the number of states are more. Now we will see how to formulate the states. So first of all we will take a state x1 equal to y1, that is displacement y1 is represented by x1. Now we can write x1 dot equal to y1 dot, that is equal to state x2, and then here we will see we require y1 double dot, therefore we can take y1 double dot equal to x2 dot. So here in the first equation we have taken 2 states. Now coming to the another equation, that is this equation, equation 4. So for this equation also we require 2 more states. So we write down as x3 equal to y2, and this x3 dot equal to y2 dot, and this x3 dot equals to y2 dot. So that can be assumed by another state x4, and therefore y2 double dot equal to x4 dot. So assuming all these states, we have covered both the equation 3 as well as equation number 4. So now we write down the equations in terms of these states. So our equation will get m1 x2 dot plus b into x2 plus k x1 minus x3 equal to 0. Now this is equation number 5. Second equation m2 x4 dot plus k x3 minus x1 equal to f of t. This is equation number 6. So we have written equation number 5 and 6. So now we want the equation in terms of state space model. Therefore what we will do, from this equation 5 we can write down as x2 dot equals to minus b by m1 into x2 minus k by m1 into x1 minus x3. And similarly from equation 6 we can write down as x4 dot equal to minus k by m2 x3 minus x1 plus f of t by m2. And another state, that is we have taken x1 dot equal to x2 and x3 dot equal to x4. So here we have got x2 dot, x4 dot, x1 dot and x3 dot. Now this we have to represent in a state space form. So how will we write down state space form? So we write down as x1 dot, x2 dot, x3 dot and x4 dot, that is equal to, so we get the elements of A matrix, the elements of x1, x2, x3, x4 plus we will get the elements of B, that is U means here force f of t. Now what is x1 dot? So x1 dot here is equal to x2, so we write down 0 1 0 0. Now what is x2 dot? So we will find that x2 dot equals to minus b by m by x2, k by m on x1 plus k by m into x3. So we can write down as k by x m1 minus b by m1, k by m1 0. Similarly we write the elements of x3 dot. What is x3 dot? x3 dot equals to x4, so we can write down as 0 0 0 1, and lastly the elements of x4 dot, you will find that the elements of x4 dot, these elements concerned with the force f of t. So, we can write down as, first of all we have 0 0 0 for remaining this state x1 dot, x2 dot, x3 dot, and particularly for x4 dot we can write down directly 1 m2. Now, about the other elements we can write down as k upon m2 0 minus k upon m2 into 0. Now, about the output. So, there are two outputs. So, here y1 and y2. So, y1 equal to x1, x1, x2, x3, x4. So, here 1 0 0 0 and here y2, that is equal to you have x3, that means we can write down as 0 0 1 0. So, this is the state space model of a mechanical system. So, similarly you can try many more examples and try to develop the model. But here we find that if you draw the free body diagram, if you take many higher order systems or many masses being a damper, it is sometimes very difficult. So, in the literature there is one method is called nodal analysis method. So, that method can be also useful to get the state space model. So, first of all we will see the nodal analysis approach. What are the steps to be followed? The step 1, the total number of nodes equal to total number of displacement plus one reference node in addition. Then step 2, in step 2 we will see that as there are mass, spring and damper, particularly mass m, is to write, we have to represent like this: mass m has one displacement, it is to be connected between the displacement y and the reference. And about the spring and damper, so spring and damper have two displacements y1 and y2, and it is to be connected between y1 and y2 or with reference to reference node. And lastly, step 4, after drawing the nodes, force equation can be written for each node. So, these are the steps which is to be followed to get the model of a mechanical system. Now, we will see the same example and try to find out the model. Now, we take the same system again. Now, here is damper, here is mass m1, then this is a spring, then we have mass m2, force f of t, then displacement y2, displacement y1, this k and b. So, same system we have taken and I had redrawn it. Okay. Now, the step 1 say that total number of nodes equal to total number of displacement along with one reference node in addition. As you see that in this problem there are two displacement y1 and y2, and therefore, we take one reference node addition. So, total number of nodes in this case, that is 3. So, we will show it, and again the second thing about the mass m1 and m2, mass m1 we have to show with respect to node and reference, m2 we have to show with respect to node and reference, then this spring k is between the two nodes, that is y1 and y2, and b is only concerned with the node y1. So, node y1 y2, displacement y1 y2, total number of nodes are 3. So, we are showing, so first of all we are showing node y2 here because we have to apply the force. So, I am showing y2 here and y1 this side. So, here y1 is the node. So, first of all, what is the first step? You connect the all the masses connected to each node. So, always mass are connected between the node and the reference. So, this is a reference node. So, here I am connecting mass m2 and here y1 we are connecting mass m1. Now, where the force is applied? The force is applied to mass m2, that represented by node y2. So, here I am showing the force applied f of t, and corresponding to this is spring is connected between y2 and y1, and here one damper is connected B here. So, this is a diagram using nodal analysis approach. Now, this is spring K. Now, we have to apply the equation of motion. So, force is applied. So, incoming, outgoing. So, force is applied to node Y2 and this is outgoing. So, incoming, outgoing, just like incoming current and outgoing current in electrical circuit. So, here we write down the equation as F of t equal to mass m2 d square y2 of t dt square plus k, this k, y2 minus y1, this is y2 of t minus y1 of t. So, here we get this is equation number 1. So, all these things we have shown, f of t we have shown, then this mass is shown and this spring part has been shown. Now, applying the force equation to node y1. So, for node y1 we write down m1 into m1 d square y1 t by dt square. See here for this mass, here for this y1 the applied force is 0. So, now we are only showing first of all for m1 and b1 and force we take as 0. So, m1 d square y1 t by dt square plus k. Now, for k, now here we are showing like this from this side. So, your equation is y1 t minus y2 of t plus b ddt of y1 of t equal to 0. Okay. So, these are the equations and now what we write this equation in terms of m1 here y1 double dot, if write this equation plus k y1 minus y2 plus b y1 dot equals to 0. And about this equation f of t equal to f of t minus m2 y2 double dot minus k y2 minus y1. So, these two equations we obtain and you find that earlier also we have got these equations, that is whenever we apply the nodal analysis, first of all you have to see how many maximum displacement, take one reference node addition, then apply the force and see where the force is applied, take that force, and whenever the force is not been applied take it as 0 and then use the convention of the mass with respect to accelerations, then damper is with respect to velocity and spring is with respect to displacement, and we have to write the equation and we can get the model of the system. So, these are few references: Ogata, BC UA Bakshi and VU Bakshi control system technical publications. This is for PHI and this is for modern control, this is for Pearson. Thank you.